If you are an A-level student, you must know about the most famous compound in organic chemistry, methane, right? That's what you are seeing on the board. Now, also from your very first class in organic chemistry, you have been told that carbon makes 4 bonds, and you can see that carbon is making 4 bonds with 4 hydrogens in the molecule methane. Okay, but today I'm going to prove to you that with the basic rules and principles of atomic structure and atomic bonding, carbon should actually make 2 bonds and the compound should be CH2. Let's see. First of all, let's write the electronic configuration of carbon in ground state. We know that the configuration 1s2, 2s2 and 2p2, right? If I show you the orbitals here, so for the s orbitals we have 2 electrons there, and for the p orbitals we have electrons in px and py. Let's say this is px and this is py. We have unpaired electrons. Now we know that to form covalent compounds, covalent bonds, an atom must have unpaired electrons available, right? So our carbon has unpaired electrons, but it has 2 unpaired electrons. That is, one of them is in px and one of them is py. So electrons from another atom will be shared here and shared here, and they will form covalent bonds. So according to the figure, just look at the diagram, carbon should make 2 bonds and the compound that should form is CH2, right? But CH2 is very unstable, hence CH4 is formed, and it does not make any sense. So how does an atom like carbon, which has only 2 unpaired electrons, are forming 4 identical covalent bonds? That's where hybridization comes in. So to form 4 bonds, carbon needs 4 unpaired electrons, right? That's why what happens is carbon goes through a process called excitation. What happens is carbon absorbs a little bit of energy and pushes the electron from 2s. We had 2 electrons in there, right? Primarily we have 2 electrons in there in the 2s, and we have 1 in px and 1 in py. Our pz is still empty, right? So when carbon goes through the excitation process, when carbon is excited, absorb a little bit of energy, and that energy, because of that energy, this electron is pushed to the pz orbital. Now this electron is here. So now you can see that we have 4 unpaired electrons, 1 in 2s and 3 in p orbitals. Problem is solved, right? Now carbon has 4 different orbitals, 4 unpaired orbitals, unpaired electrons. Now carbon can go through the bonding process and make 4 bonds, right? Not quite, because 3 is from the p orbital, 1 is from the s orbital. So if right now carbon goes through that bonding process, we'll have 4 bonds obviously, but the bonds will be different in length and different in energy. Because of this 2s, it will be distinct, it will be different from the p orbitals, right? But that does not happen. It shows that the laboratory examination shows that all the bonds have same energy and same bond length. How does that happen? It happens because these s and p orbitals, they get mixed, and when they get mixed, they produce a distinct, a totally different orbital called sp3 orbital. Now as they are mixed, we call this a hybridized orbital. Hybridized. Now to understand, just imagine about that you have 4 walls to paint. You have 1 bucket of red color and 3 buckets of white color. You want to paint all the walls with the same color. How do you do that? If you use the red and the other 3 white, you are going to have 1 red wall and 3 white walls, right? But what if you mix the red color with the 3 white colors? You are going to have a distinct, a different, totally different pink color. Now if you use that pink to paint the walls, you're going to have 4 different walls with the same color, right? The pink color. That's what happens here. Carbon takes the electron from 2s, the orbital from 2s and the orbital of p's, and they mix together and produce an orbital called sp3. This sp3 orbital is totally different from all these orbitals, and we call this the hybridized orbital. Okay, sp3 hybridized orbital. Why sp3? Because we're mixing 1 part of s with 3 part of p. That's why we're getting the sp3 hybridized orbital. As this is distinct and new orbital, it has, and all of the orbitals are identical, it has the same energy and same bonds, same bond length. This is what happens here. Carbon has used sp3 hybridized orbital to bond with the hydrogen, and that is why all four bonds have the same energy and same bond length, and this is how carbon uses the hybridization process to form distinct orbital bonding.